In this video, I am going to talk about dynamic programming with powers of 2. Let's consider the following problem. How many n-digit numbers have a digit sum of 0 modulo some integer d? And for simplicity, let's also consider numbers that start with one or more zeros. You will be able to eliminate this assumption if you understand this video. Dynamic programming problems usually involve two steps, and the first step is often solved by the problem statement itself, which involves associating a function to the problem and defining that function just in plain English. Next, we will write a recursive formula for step 1. We can let dp of n and k be equal to how many n-digit numbers have a digit sum of k modulo d. And here's a pro tip. If a constant shows up in the problem statement, such as 0 here, then see if you can make it a parameter for your function. We did that with k here. So basically, we generalized the 0 to a k. Now for the math. The second step is usually the tricky one, because we will always need to write some mathematical expression for it. In this case, the math is quite intuitive. It's reasonable to think about how we can get to an n-digit number. We can get to it by appending a digit to an n-1 digit number, resulting in an n-digit number. If you have a counter in your dynamic programming definition, like n here, then always think about adding or subtracting something from it, like we did with n here. So, until now we have dp of nk is equal to dp of n-1 and something. We need to see what we can plug in for the second parameter. But we're making good progress. So, it's quite obvious that changing the counter will probably affect the other parameters as well, in our case k. If we append a 0 to an n-1 digit number, then k will not change. So we get dp of nk equals dp of n-1 k. So is this it? Are we done? Well, unfortunately not, because 0 is not the only digit that we can append. Always make sure that you've covered all cases in your recursion. If we append a 1, then the n-1 digit number must have a digit sum of k-1 mod d. That is, if we want to end up for the n-digit number with a digit sum of k mod d. And a similar reasoning applies for the other digits as well. So our recurrence will be dp of nk is equal to the sum over all digits from 0 to 9 of dp of n-1 and parenthesis k minus digit parenthesis modulo d. This will cover all cases for all the digits. So are we finally done? Well, we're almost there because we haven't talked about the base cases. I find that it's usually easier to think about those at the end when I have the recurrence formula written down and I can see exactly what base cases should be handled. In the worst case, you can just implement it without the base cases, see where it crashes and debug it from there. But it's much nicer and a bit more professional if you do it before jumping to the implementation. So the base cases here are going to be dp of everything 0 initially, so you should initialize a dp array with 0, and increment dp of 1 and digit modulo d by 1 for all digits. You might run into edge cases in your implementations, but these should be quite easy to debug, and you can also check the GitHub link for my own implementation if you get stuck anywhere. Of course, the final answer after computing all this will be in dp of n and 0. Now, what about the time complexity? Well, it's quite obviously order n times d. We can get more exact with n times d times b if we have b digits, but I don't really want to focus on this detail in this video. We're dealing with base 10 here, so b is a constant. It's quite a large constant, but a constant nonetheless. The bottom line is that this is quite bad for very large n and d. So, can we do better? Well, there's never any free lunch, but we can focus on making it better in some cases. And we're going to take the following case. A very large n, 10 to the power of 9 or so, that's about a billion. And not so large d, let's say 100 or so. So what can we expect to get with those assumptions? Well, when you have such large limits, you need to think about logarithmic time complexities. Can we do order n log d, for example? Well, even if we could, that n is still way too huge. So we're left with order d log n, order d squared log n, order d log squared n, something like this. The idea is to have a logarithm on the largest item, which in our case is n. Now we need to get creative with our function definition. The problem statement alone won't cut it anymore. Think about what generates a logarithmic number of steps. Binary search, for example, cuts the search space in half at each iteration. If we can do the same, we'll have our logarithm. So let's try to define something that cuts n in half at each step. Let dp of k and j be equal to how many 2 to the power of k digit numbers have a digit sum of j modulo d. Let's assume that n is a power of 2. If we can compute this, the answer will be in dp of log base 2 of n and 0. There isn't any exact way to think in order to arrive at this. Ultimately, it just comes down to intuition and experience. So, the math. We know that 2 to the power of k is 2 to the power of k minus 1 plus 2 to the power of k minus 1. So dp of k and something will depend on dp of k minus 1 and another thing, and dp of k minus 1 and yet another thing. So now we must figure out those somethings. Note that for every 2 to the power of k minus 1 digit number that sums to s1 modulo d, and by sums to I mean the digit sum is s1, we can pair it with all 2 to the k minus 1 digit numbers that have a digit sum of s2 modulo d, obtaining a 2 to the power of k digit number that sums to s1 plus s2 modulo d. So our recurrence will be dp of k s1 plus s2 modulo d is equal to the sum of all dp of k minus 1 and s1 times dp of k minus 1 and s2 taken over all s1 and s2 between 0 and d. Think about this as two nested for loops going from 0 to d and doing plus equals on the left hand side. The base cases will be similar. We should initialize dp with 0 initially and increment dp of 0 and digit modulo d by 1 for each digit. The time complexity of this will be order d squared log n, which is good enough for our constraints. And as a bonus, notice that there is no b here anyway. even if we considered it a constant before, it was quite a large constant anyway. Here it doesn't show up anymore, so we've actually cut down on a large constant in the complexity, whether or not we want to hide it. Okay, but what if n is not a power of 2? Well, let's write n as a sum of powers of 2, or its binary representation. And the same idea will apply. Let dp2 of I and j be equal to how many 2 to the power p1 plus 2 to the power p2 plus ... 2 to the power pi digit numbers have a digit sum of j modulo d. The final answer will be in dp2 of k and 0. The math for this recurrence is very similar, and I will leave it as an exercise in this video. Don't worry though, I also hate it when people leave stuff that I can figure out as an exercise, so you can find it in the GitHub code I linked in the description if you can't figure it out. There are a few implementation details that are worth going over, I feel. First of all is that the answers in both DP and DP2 and both the first approach and the second approach will be huge. So one thing you can do is compute them modulo something. For example, modulo a large prime like 666,013. Especially in Python, this is very important because Python will allow for huge integers, but it will take a long time to compute them. So it will be much faster if you do things modulo something, especially if you use NumPy. For example, using NumPy and its np.int64 data type will help. You could also just do it in C. It will definitely be faster that way. Other optimizations are also possible. I've done a few things in the code that I've commented and given some hints about how they can be improved. So I do suggest that you read the code for further details and exercises, and please leave a like and subscribe if you enjoyed this video.